How many data scientists in chat have gone through some sort of clustering phase? I'm in my clustering phase. Clustering NHL players by usage. A very interesting breakdown of how he wants to build a hockey team. Rick places a player in each lineup spot, and that has the skills he wants each player to have. I find this very interesting and smart way to build a team, as it fits with how we think of players having unique skill sets. To explore this idea more, I set out to learn and classify players based on how they are used by their coaches. I decided to cluster players based off usage stats, and evaluate those clusters to gain an understanding of basic categories into which players are placed. You know, the writing is like a 7 out of 10, 6 out of 10 in terms of flow, but I get what he's saying. This person's gonna go on a clustering expedition and then some descriptions of the clusters they get. I think every single person in their, data science or analytics journey ends up doing a problem like this, whether it's early or late in their career. It doesn't matter. Everyone does a project like this where you end up getting into clustering. Like everyone has like a clustering phase. You know in high school where like you had that like metal phase or that pop punk phase.
It's not a phase, Mom.
Yeah, maybe you got really into wearing like Hawaiian shirts. In data science, same thing. You're gonna have like a phase where like you make graphs with like 538 color scheme, and then you get really into clustering, XGBoost phase.
Like the PCA phase every beginner goes through.
That's right. How many data scientists in chat have gone through some sort of clustering phase? I'm in my clustering phase. I'm not saying that these things are bad things, Like I made an entire career in late GBM. I made a game where people gamified XGBoost. All right, let's take a look. So here's all the features that they use in their clustering. This is all hockey related stuff, so I really don't know what the hell the majority of this stuff is. TOI is this time on ice? Measures the proportion of ice. Oh yeah, time on ice. So this is like time that they're playing. The average XGR differential of a player's competition. Yeah, I don't know what the AR stands for, but XG is expected goal. Goals above replacement, that's what the AR stands for? Goals against randos. So let's do some dim red. Does anyone call this dim red? So they take all these features and they shove this through a UMAP. If you're unfamiliar with UMAP, that's, as it says, dimension reduction. It is a non-linear way to do dimension reduction. If you use something like principal component analysis or independent component analysis, those are linear ways to do dimension reduction. With a lot of problems, you can probably use ECA or ICA, and you're going to get, for the most part, what you want out of it, which is a smaller set of features. In this case, if you have like truly nonlinear features and there's like little to no linear interaction between your features, but they're supposed to like, sum to some sort of signal, you could use something like a dimension reduction, and this does a pretty good job at finding those interactions for you. Now, the issue with dimension reduction is the purpose of dimension reduction, and we should really remember like why these things are created in the first place before we like think about using these in our own practices, is to do what it says. Reduce the dimensionality of your feature set. If you work with like very wide data, right? So for me, I worked with really wide data. Say you're working with fMRI data. So every pixel, really every voxel, is an area that you're trying to assess for blood oxygen concentration. So every voxel that you have is its own feature, its own column of data, and that runs over time. And your voxel density can be really, really, really dense, 100,000 plus features, right? If you wanted to capture all the voxel space available. So how do you work with 100,000 columns running at an hour long, sampling at maybe a sample or maybe two samples every second, something like that? Well, one thing is maybe you don't have to assume. Maybe you can let a machine do that for you. Here comes dimension reduction, where they will take all your features and create what's called components out of them. These components ranked from 1 all the way down to n. The top handful of components can represent up to 95, maybe 99% of the signal that's coming from data. You know, one of the original reasons we use this is to take really wide data and to ultimately it's a technique for downsampling. However, some people out there have gotten pretty creative with the dimension reduction techniques, and they use dimension reduction in a way that's more similar to clustering. So rather than taking a large set of features and reducing it down to a handful of features, a lot of people might take a handful of features, a smaller set of features like this, and using the clustering, the components that you get out of them, those components may have just inherent explanations to players because these statistics that are in each of these components are like in some way. They're trying to put like data together. And so you come out with different components, different columns of data, and they look like this in a embedded space. And so you can see this person is going through like the steps of what a typical person who's gone through UMAP and then into their k-means clustering. They've taken their UMAP. They have some sort of set of k-means based off of their original data set. And so now they're trying to see where people fall. And then ultimately, they're trying to describe sort of these different clusters that come out when plotted against the UMAP embedding. Some fancy clustering mechanics here. The UMAP has sorted our players into, given the unique shape and the embedding. I chose to use a Gaussian mixture model, which aims to find multiple distributions within the data and return a distribution to which each point belongs. Okay, so what are these four clusters? Given the statistics, what are these four clusters and how does the data look when we try to see what the averages look like? This isn't the best graph for this, but it's pretty good. The top six, these players face good competition with good teammates and are deployed in all situations over the ice. The inherent bias here, in terms of UMAP or any dimension reduction, you're trying to, like, it's not too different from any other, like, clustering type process, but they're trying to get like things together. And if you have a feature that is, say, overfitting your data in some way, then it's gonna dramatically overfit. We might not necessarily be seeing any overfit here, but that is always like a concern. Like, good competition with good teammates are deployed in all situations. Bottom six are these players face below average competition with below average teammates, and while getting used in all situations all over the ice, they get used much less often than everyone else than every other cluster. They are the jack of all trades, but seemingly master of none. Wow, brutal. Then you have defensive specialists and offensive specialists. Their tell here is, I guess, the goals. So these players, defensive specialists, play slightly below average competition with worse teammates than their opposition and get a lot of penalty kills and defensive zone start opportunities. And offensive specialists face above average competition with better teammates and have a lot of power play and offensive zone startup. There seems to be like a weird thing of like certain players or like offensive players are also like inherently playing against good players, quote unquote, right? And defensive players and not good players playing against worse opponents. So I wonder, like, what about good defensive players? Where do they fall? Jesus, what the hell's going on in this chart? Below is a chart in how each cluster distribution compares to other clusters in each stat. Isn't this just this, but in box plot, in like stacked box form? Oh, year over year player development type changes. Oh, some Sankey in here. I could tell by the colors this was a Plotly Sankey. It seems like the top players end up migrating away, but it does get filtered in with a handful of other players, specialist players who end up becoming top players. And there's little room for a bottom six player to become a top six. Okay. This is matching up with some intuition. This is interesting. This is like a very complete dive into clustering, different clustering techniques, and then ultimately like some sort of finding based off your clustering methods. In this case, the method was
Damn son, where did you find this one?
Dude, it's in the React channel. People just throw shit in there, you know? I like this one. This is a pretty good, like, top level clustering walkthrough. I would say this is pretty complete, and it's fairly, like, forward. So it doesn't start you off with any fluff. Like, you're diving straight into UMAP. You're going from UMAP and doing k-means, and then into a GMM. From that GMM, you're popping out like some sort of like subjective way to describe your clustering. And then that's typically where the art comes in, you know, in the clustering world. You tend to have to use your domain expertise at this point. Like once you have your clusters and they're separating clearly, then you gotta be like, all right, what the fuck do these clusters mean? So yeah, this is nice. This is a good little walkthrough here. Everyone has a clustering phase, y'all. Everyone has a clustering phase.